Okay, then let's start keep sampling. Okay, so then we have this code. Okay, CLC clear. Okay, RNG is 16. It doesn't matter. And then you have your own edge path, right? Then suppose you have three slope coefficients. Okay, so beta 1, 2, and 3 only. And then the true values are 1, 2, and 3. Okay, 1, 2, and 3. We have three true values. True beta 3. Okay. Of course, this is 3 by 1. Okay, 3 by 1. Okay, and true sigma square is 2. Yeah, and sample size is 100. Is okay. And we have three exogenous variables, x1, 2, and 3. Yes, and so x must be a matrix of x1, 2, and x3. Right? Okay, so then this is the DGP, and then we are not going to use the OS. Yeah, actually we will, because we are going to compare the estimated result from the OS and keep sampling both. Okay, so then let me run it first, just to make sure it runs where. Yes, it runs, right? Okay, then okay, but we are going to do this later. Okay, so then let me put percentage here. Okay, okay, so now here gives sampling. Keep sampling. To do this keep sampling, what do you have to do? We have to specify what? Prior. We are going to specify the prior or hyperparameters, right? And then the next is posterior sampling. Okay. So that means hyperparameters. Okay. So then, first of all, beta 0, which is what? Posterior mean. And then we don't have any specific prior information for the betas. Then usually the posterior mean of beta is specified as zeros. And how many parameters? We have three parameters here, right? Three betas, right? Beta 1, 2, and 3. 0, 3 by 3, 1. And what about its variance covariance matrix? So B0 is what? B0 must be what? It must be 3 by 3 matrix. And then I would say identity matrix. 3 by 3 identity matrix. Okay, and then, but I don't have any strong prior. So then let me multiply, say 9 times identity matrix 3. So then prior variance is what? Prior variance is 9. Okay. And now alpha 0 and delta 0. Alpha 0 and delta 0 are the hyperparameters for sigma square. So then I'll say that 5 and delta 0 is also 5. Okay, 5. Right. So then, right. So it means what? The alpha 0, delta 0 are both 5. It means what? So for example, the prior mean is determined as delta 0 divided by what? I'm sorry, 0.5 delta 0 divided by 0.5 times alpha 0. 0 minus 1. Right? So then in that sense, 5 looks quite small. Let's say 8 and 10. 8 and 10. So then it means what? It means what? It means what? 0.5 delta 0. It means 5 divided by 4 minus 1. Right? So that means 5 divided by 3. Right? So this is a bit less than 2. Right? True value is 2. And our prime mean is a bit less than 2. Okay? So that's it. Then, okay. Then MHM is the storage for saving the parameters, zeros. We'll say n comma 4 in this, because we have 4 parameters. N is what? N is the burn-in, n0 plus the simulation size after the burn-in, n1. So then n0 is 1000 and n1 is 10,000. So this is burn-in size. Burn-in size. This is simulation size after or beyond burn-in. Burn-in. Okay. So, and this is total simulation size. That's right. So then, now what do you have to do? Let me go back to the algorithm. Okay, what do you have to do? What do you have to do? Now, we have to specify initial values for sigma square, right? What's the initial value? Prime mean. So then, initial value, I would say sigma square. Sigma square's initial value is here. Right? So this is initial value. Say this is initial value for sigma square. Okay. This is the initial value for sigma square. And then also we have to define alpha 1, B1, A, right? So then alpha 1. So the alpha 1. Alpha 1 equals what? Alpha 0 plus what? Sample size. Sample size is what? Rows of y. Right? Rows of y or rows of x. Okay. So then what's the next? What's the next? B1. B1 is s prime x plus b0 inverse. Inverse. Right? So then here B1 equals inverse of what? X prime times x plus inverse of what? Inverse of B0. Right. So this is literally B1. And what about A? What about A? A what? X prime y plus B0 inverse beta 0. Right? X prime times y plus inverse of B0 times beta 0. Where is beta 0? Beta 0. Beta 0. This is literally A. This is literally B1. Right? B1. Okay. So then you see that B1 times A is the full conditional mean of beta, and this doesn't change over the iterations, right? So then let me compute B1 times A first. Okay, so then posterior mean, I would say, so then let me say this beta 1. Beta 1 equals B1 times A, semicolon. This is what? This is full conditional mean of beta. Okay, mean of beta. Okay, this is fixed over the iterations. That's why it's computed before the iterations. Okay. Okay. So then let me go back to this algorithm. You see that we have to repeat very similar computings, right, many times. And whenever we have to do this, we are going to use for loop, right? For loop. For ITR equals 1 colon n, end. Okay, this is for loop, and then within this for loop, there are two steps. The first step is beta sampling. The second step is what? Sigma square sampling. Right? Sigma square sampling. Okay. Then let's do the beta sampling first. Okay. Again, where is the algorithm? Here. Mean is B1 times A, which is beta 1. We have beta 1. And sigma square times B1 and normal, right? So then, okay. So right. So then say beta equals beta 1 is mean plus rand n. How many parameters in beta? 3, 1, right? But variance covariance is what? Variance covariance is what? Variance covariance is what? Sigma squared times B1, right? Sigma squared times B1, right? So then, but this is what? This is standard normal. Standard normal. So then, to get the normal draws from this distribution, this mean should be added. It has been added already. Here is beta 1, and then the variance is here. Variance covariance is here. So if this is scalar, we have to multiply what? We have to multiply square root of this value, right? But this is matrix. Then the square root of matrix is called Cholesky decomposition. Sure. And C2 times B1 times rand n 3,1, and this gives what? This gives the upper triangle matrix. But what we need is lower triangle matrix. Then to get the lower triangle matrix, we need to put this transpose, which is prime. Okay, so just to make sure that Chor is upper triangular. But what we need is lower triangle matrix. That's why we have this prime. Don't forget transpose. Okay, so this is beta. Okay, this is beta, right? This is beta. Then, what about the sigma square? Sigma square is what? Sigma square is generated from inverse gamma distribution. Inverse gamma distribution, and then this rand rand inverse gamma ig. But rand ig is not a built-in function in MATLAB. So I have created my own where is my own inverse gamma distribution. So the this must be okay. It must be in my library. Where is it? MATLAB. That's M on the library. Rand ig. Okay, rand ig. Okay, let me copy. Okay, let me copy, and then okay, go back to here. Where is it? Where are we? Oh, here. And then MATLAB, let me save it to my library and paste it. Okay, so then this can be called whenever we want. Okay, so then the parameters are what? Alpha 1 divided by 2 and delta 1 divided by 2. But what is the delta 1? What is delta 1? Yeah. What is delta 1? Right, delta 1 is defined what? Delta 0 plus sum of residuals, right? Y minus x times beta prime times y minus x times beta. Yes, all right. Then, yeah, I think we are almost done. Okay, just to make sure it runs, let me try to run it. Let's run. Change folder, of course. Randgam. Randgam. We need randgam. Okay, so then let's take a quick break.